Good morning to all the participants of this ABCD transfer workshop. At the outset, let me place my thanks to the ABCD Center for giving me an opportunity to share my experiences with you. The topic of the day is multifunctional marine structures in the era of climate change and blue economy. The contents of the lecture is what is blue economy, sectors and importance, country-wise performance till date, structures in the marine environment for effective use of the resources. I'll move on to multifunctional or multi-purpose structures, which will involve wave energy converters to be integrated with coastal protection structures or pile supported structures for intermediate water depths. Based on my discussion, I'll conclude with a summary. What is blue economy? World's coastline is a hub for trade, energy, fisheries, as well as tourism. Alignment with blue economy, that is a vision for alignment of blue economy, should be use plus sustainability and associated with growth. In order to fulfill the above objective, we have to also consider the impact of the climate change on the marine environment, which are associated with the sea level rise, extreme events like cyclones, typhoons, tsunamis, and storm surges, which increase the frequency as well as its magnitude, leading to coastal flooding and other coastal damages. Ocean acidification and temperature rise, impacts of behavior of materials under marine environment is a very important topic that needs careful attention. Last but not the least, I have listed the common problem of erosion as well as sedimentation. Erosion is more common than sedimentation because sedimentation is more problematic near approach channels of harbors and confluence of rivers and ocean, whereas erosion can be anywhere along the coast, which immediately pinches the livelihood of the coastal community. When you look at the blue economy, if carefully used, is the sustainable ocean resources for economic growth, improved livelihoods, and ocean ecosystem health. You have to be very careful not to use the word exploit, which was very commonly adopted in the past while talking about the ocean resources, non-living ocean resources. Should focus on balancing economic benefits with environmental sustainability and social equality. Now, the blue economy, it has a wide scope for us that includes maritime transport, fisheries, renewable energy, tourism. But when you want to make use of all these things, you have to also be careful with the climate change, how it is going to affect the environmental changes, particularly the coastal environment, and also the waste management within the ocean, as well as dumping of waste from the land into the ocean. Top countries and regions funding into blue economy. As you can see in this picture, the dark blue is the one which is uh, which is ranked as per the darkness of the blue color, which indicates the Nordics are the countries with the most share of funding going into the blue economy. Added to this are the countries Portugal and Mexico. But if you look at Far East, there's not much, for particularly the coast of India. We don't have much of funding into the blue economy, although now things are changing and we are looking at in a different. Now we see the structures that support the blue economy for the sustainable use of ocean resources. These structures can broadly be classified as nearshore structures, port and harbor structures, and offshore structures. With the nearshore structures, you have a variety of structures which are breakwaters, seawalls, revetments for bank protection, groins for coastal protection, intakes and outfalls, and artificial reefs. And application of geosynthetics have become quite common these days. And a number of structures can be constructed using geosynthetic products. Port and harbor structures, you have wharf, quay, pier, jetties, sheet pile, dolphins, trestle, which all put together can form a major harbor. And a view of that harbor is given below, shown below. Then when we see the offshore structures, we have broadly two classified types. One is the bottom supported and the other one is the floating units. Under the bottom supported, you have jacket structure, gravity based and compliant structures. And in the case of floating units, you have semi-submersibles, spar, FPSO, etc. And I don't want to go into the details of the structures. Now, monitoring the stability of a shoreline is mandatory, which many for many stretches people forget after implementation of any coastal structures. On to the left, you see the erosion that is in progress. On to the right, you see what happens even if you have constructed a seawall to protect the coast from erosion, but then if the coast is vulnerable and if the sea weather is a sea wave climate is severe, you can have the coastal flooding, as you can see in this on the right side video clip. Now, when we have to handle this kind of a scenario, we do have strategies to counter these type of extreme flows. They are all well documented, and it is not so easy to, no, it's not so difficult to design these structures. But then careful monitoring is extremely important. So you have a broadly classified measures like the hard measures and the soft measures. Added to that, we have a combined countermeasure, that is combining hard and soft measures. And there is a future direction. For example, we are working on what is called as the buffer blocks. As you can see here, these are all buffer blocks, which comes under the dam engineering. You know, under the spillway, you have the buffer blocks in order to dissipate the incident, dissipate the flow which is running down the spillway. So under the hard measures, we have the structures, breakwaters, seawalls, and dikes, and then also the groins come under this category. So groins are the structures, as you can see, they are shore-based as well as seawalls, and there are some inherent problems in this, but you have to keep monitoring the structures. But the design is not so difficult, but only thing is you have to be very careful while before designing whether you want to have a groin field or the seawall or this. In structures, in locations where you have the stretch of the coast being dominated by the longshore sediment transport, then these will be the ideal solutions, whereas this will be for locations where you have the cross flow very high, and also the idea is to prevent coastal flooding. In that case, seawall is much better. Flatter the seawall, it will be more beneficial, but then it occupies space, as well as the budget is also going to increase. So you have to strike a via media between these two. And other aspect after the tsunami, which has become very popular, are the vegetation belt, which we have done considerable amount of research into this area, and still my colleagues are working on this problem. Now, moving on to multifunctional coastal structures, the idea is to protect the coast, and it should enhance the biodiversity and marine habitat, improve the water quality, and it should be nature-based development, and it should also facilitate recreation and aquaculture. And then finally, if you can integrate wave energy converter into some kind of a structure, and also a structure that can allow berthing of vessels, and also linked with wave energy extraction device. So the last one is the one which I will try to concentrate later. And achieving all these things is quite a challenge. It's not so easy. But anyway, we have to, our efforts is now more towards the last item, which I will be focusing. Broad types of multifunctional coastal structures. We have all this, the broad list is given here, living breakwaters, etc. All this, the entire structures, whatever we have discussed here, comes under nature-based solution, in fact. But the purpose in general is to create some kind of a porous medium that can facilitate the flow of water into the porous medium, thereby reducing the intensity of the flow. And also this kind of porosity can facilitate the biodiversity and marine growth, and etc. So I will not touch upon this, because there are going to be some a few more lectures on the nature-based solutions, but I'll move on to the next. Now, how can we convert the sea walls, which are very commonly adopted uh, along the most coast of the globe, where you see the simple structure is dumping of stones along the coast with a natural slope, which is not good. But we now then that was the initial stage when when people were desperate in protecting their coast. Then later, the scientific way of designing the seawall came into picture, where the slope of the seawall, as well the size of the individual rock, play an important role in deciding the cross section of the seawall. But then when you have a cross section seawall alone, then it becomes an eyesore, and the people will not venture into the ocean, and it is like you are surrendering yourself to the attack of the ocean waves. So you will not venture into going and seeing the ocean. So instead, we have to have some kind of benefit when you are constructing a seawall. And one such thing is what we call is a boardwalk. As you can see, it is quite popular in a number of other countries, where you see that the seawall, the dumping of the cross section of seawall is not visual, it is not visible, and it is just below the platform, where people can walk around, or they can do fishing, jogging, etc. And there are some locations where you adopt step type sloping walls, and with slits that can promote the dissipation. And there are some marinas also that can be so you have the multi-purpose. Here you see there is a concave type of surface, where this kind of a wall uh, will push back the incident wave energy back into the ocean. And so it would be nice to go along this road, I'm sure. Then, based on this, we have designed along the Kerala coast, which is in the pipeline and which should be taking off shortly. So that is in basically the essence of seawall that can be converted into multi-purpose seawall instead of just using dumping of stones to form a particular cross section. And we have the other common structure, which is the groin field. Groin field. There are a lot of groin field along the coast. For example, the entire coast of number of coasts along the coast of Italy and other European countries have been protected by the groin field. And now you see that what we have done is this is a stretch of the coast, a tip of somewhere close to the southwest coast of India, where this area was frequented by the index of flooding, coastal flooding, and there was a need for protecting this coast, and we thought we will go in for a groin field after assessing the nature of sediment transport, and we found that when we did the calculation, the sediment transport was quite appreciable along this coast, and hence we decided to go in for the 6 groins as you can see here. One, please note that there is an outcrop here which we did not really take into account, or we thought it may not have much of influence, and then from a hydrodynamic point of view. And then what we did is when we went on to construct, then we decided we were forced to take a decision at the site. For example, there was an urgent need for the local people to join this one of this groin to this outcrop, because there is a church here, and the people wanted to use this at the top of the groin to reach the church. So we examined again with the numerical model to see if there is any adverse effect that can happen, and we were convinced that it can be joined, and we joined, and now you see this is what has resulted, and this is the kind of beach that was found, and it's a great successful project, and even today it stands as it is. And also these beaches have started being used as beach landing facilities. This enabled the governments of state of Tamil Nadu and Kerala to entrust the responsibility of preparing the tsunami signature studies as well as the mitigation plan on us, and we did that in a record time of 3 months. So groins cannot be the only solution everywhere, as I said earlier. So for example, this was the tip of the Indian peninsula, where they had constructed in mid 70s the number of groins, about 7 groins, but that did not yield any result, and there was no formation of beach as they anticipated. This was taken during the 2004 signature studies after the tsunami. So early 2005. So you see that this was not giving any result. So what we did is there was an ingress of water during the tsunamis. They wanted some kind of a protection measure, and hence we decided that one of the the southernmost groin can be extended as shown here, so that the top level was maintained as something like plus 4.4, so that in the event of a tsunami, the inundation distance as well as the height can be reduced because of this obstruction, and at the same time this can also be providing as a harbor for the local fishermen, and people are quite happy with this. Having said about the basic structures on its multi-purpose aspects, then we move on to ocean energy, the state of art. That is, the ocean has at least 6 forms of energy to us. That is marine current, offshore wind, ocean thermal energy conversion, waves, salinity, and salinity gradient, and tidal gradient. So now, although we have 6 forms, among this, wave energy has a number of advantages, and it has been widely being recommended, and there are a lot of pilot plants, commercial plants which are available in the globe, around the globe. Now, when you look at the distribution of wave energy around the world, you see that this area around the European nations, particularly along the North Sea and some parts along the US. You have a good amount of wave energy, but when you see around Indian coast, you see it's only 14 compared to about 70, 60, etc. That is in terms of kilowatt per meter. So, being a very less amount of energy, but still we wanted to. But this was during early 80s when the entire all the most of the research was being concentrated on wave energy. We wanted to work on that, but at that point of time, I published my paper, first paper in 1986, wherein I said that the wave energy converter is wave energy extraction from extraction of energy from waves. It's not so may not be so fruitful, and if you work out the cost benefit ratio, it may not be so appreciable. So this is what I published, but then we went ahead on implementing the pilot plant, and only to know that we had installed the pilot plant, but then of late you see the entire globe also research, there was a slowdown in research on wave energy from say maybe 2010 to 2020, and after 2020 or late around after 2015, you had again a lot of interaction, a lot of research going on, and also again started off. And when we started, we thought we should concentrate not standalone wave energy, but try to integrate it some other purpose for some other purpose. So based on this, this was published my paper on the conceptual design of integration of OWC, that is oscillating water column, into breakwater. This was published during my stay with the Norwegian Institute of Technology, and this formed a base paper for several authors who have been investigating. So the advantages is functional multifunctionality, cost sharing, enhanced performance of the structure, space optimization, minimize shoreline erosion. That was the basic idea with which we started. And then what exactly is the wave energy converter? So we are talking about the oscillating water column. As you can see this on the left side, you have a cliff, and it's just a small hole under which the waves are moving in. When these waves are moving in, you see the amount of air that is coming out. So on and off you have the air coming out, and that can push a turbine to generate electricity. This is the basic concept. And now how can we have an engineering design? The engineering design can be a vertical wall, front wall, or slanting wall, as you can see here, allowing this to move. And this is the chamber, oscillating chamber, and this is the air which is going to oscillate because of the oscillation of the water surface, and that oscillation is going to run a turbine. That is the concept, basic concept with which it's a well-known concept. So how do we integrate this wave energy converter? So we have seen that the offshore detached breakwaters, which is another concept which has been widely adopted around the globe for protecting the coast against erosion. And now, how about integrating this OWC into this rubble mount breakwater? That was our first thinking. So this is the rubble mount breakwater, and this is the cross section of the OWC on the sea side, and this will be as on the lee side. And then you see that we have placed a number of OWCs within the one section of the rubble mount breakwater, and you see the oscillation within the chamber. And when we did this work, we found that the natural frequency of the system is unaltered due to the change in the wave direction, which is very advantageous. And the optimum system, thrice the width of center to center model spacing, absorbs the power to a maximum of about twice the incident wave power. So, but there was an issue with this rubble mount breakwater, because what happens is if there is slightly higher energy coming into picture on the breakwater, so there can be dislodging of the individual rocks. So how do you overcome this? So then we looked at the semicircular breakwater, which has been widely used in Japan for formation of their harbors. So at the same time, we were working on semicircular breakwater, the hydrodynamic characteristics of semicircular breakwater. So now, why not we include or integrate the OWC with the semicircular breakwater? That was concept. So earlier studies led to some of the benefits of semicircular breakwater and led to the idea of integrating the OWC with a semicircular breakwater. Now, before that, what we did is we had to find out, because there can be different shapes of the OWC itself. As you can see here, it is only this one, then you have something like this, something like this. So, but we found that this is the one which has very good power extraction, or the efficiency is much higher compared to the other three. And then we decided that we have to use this for the for examining further. So the parameters that were considered are the oscillation chamber, that is the water surface which is oscillating within the chamber divided by the incident wave height, because the oscillation of the chamber dictates the oscillation of the airflow, and which is in turn going to dictate the efficiency of the entire system. And then the chamber oscillation. So anyway, these are controlled by this, because the air pressure also has to be a function of this oscillation of the water surface, and then based on this we try to get the hydrodynamic efficiency of the system. So some of these results are reported in the journal recently, that is we are talking about 2025, which is this year it was published. So we need to have some information about how it really performs. So in that way, we found that integrating this the earlier the type of structure which we have, the OWC which we had considered, we found that isolated the compared we compared the isolated OWC and the hybrid, and then we found that all the parameters we are discussing, that is the hydrodynamic, including the chamber oscillation, the chamber air pressure, as well as finally the hydrodynamic efficiency, all these things were found to be higher for the hybrid OWC, which gave us enough confidence to proceed further. Then what we did is one single semicircular breakwater, when you have OWC, how does it perform? And now, if you increase the width of the semicircular breakwater, how does it perform? So the width of the OWC and the width of the breakwater is the ratio is also very important. So that ratio was we considered three different ratios and tested, and we found that the B by W is 5 equal to 5 was extremely performing very good. So the videos are shown here for the different cases of studies we have conducted, and then some of these results are. So what we found is some of these I don't want to go into the complete details or full details, but in general we found that integrating the OWC with semicircular breakwater, which ultimately is planned for coastal protection, is quite advantages. So summary on OWC and semicircular breakwater, the results, all these results which were presented are also validated with those of the numerical investigations of OpenFOAM, which is an open source program, a software. The numerical study of 4 different isolated OWCs were studied, and then this was found to be the offering the highest hydrodynamic efficiency of about 0.7. That is quite good, because zero point 0.7 is the efficiency of the OWC, but then you also have the additional facility of additional advantage of serving as a coastal protection. Then studies on the effect of effective width of this one, we found that the width of the breakwater to the width of the OWC, if it is the ratio is of the order of 5, it gives you much better results. Then finally, two identical OWCs with the semicircular breakwater were found to offer much higher capture width, which is going to lead to higher efficiency. The least wave energy is observed for long waves as it is dissipated by more reflection and diffraction to along the lateral side of the structure. Now that explains about how you can think of integrating semicircular breakwaters and how integrating OWC with the semicircular breakwater, and how semicircular breakwater can be detached semicircular breakwater can be used as show coastal protection measure. Moving away from the coast, so you have a lot of configurations with the pile supported breakwaters, which has been widely adopted worldwide. So earlier idea was only to dissipate the energy in the incident waves. But now our idea is not just to dissipate the energy, but also to absorb. And that is the idea with which we started. But prior to that, how do we uh, reduce the dissipation of energy was studied by varying the front seaward surface of the structure instead of just the vertical surface. So all these things yielded some, this is earlier work what we had done, and we found that it was good, and now we switched on to how we can, whether what is the possibility of having a OWC in front of this instead of changing the curvature of the seaward surface. Then you see that this is the kind of animation. So on the lee side you can have a vessel that can be berthed, because most of the energy will be absorbed by this. So we found that the transmission is only 40% for this kind, and then for this kind of a structure, and the energy efficiency about 50%. That speaks, that gives again the confidence of considering this type of structures for the future. So now we are looking at other possibilities. For the example, as you can see, this is a conceptual design. We are yet to even start any work. Hopefully we'll get started soon. And we have this bottom, you see the artificial reefs, which are trapezoidal in section, which are obviously porous. So that will be serving as a coastal protection, cover protection measure for the pile supported structure, as well as it will support biodiversity and the marine growth. And that is the idea. And in fact, the Koreans have also thought of, they have another idea of having a wind turbine, offshore wind energy plant, which can also be thought of for this kind of a structure, which will be considered later. So that explains about integrating OWC with both coastal structure as well as pile supported structure. Multifunctional aspects during extreme flow mitigation measures. For example, the tsunami. Well, after the tsunami, there were a lot of discussion what could be the best possible solution. So you cannot simply raise all the structures. So what we thought is we should not be greedy in absorbing the instant wave energy, but what is needed is gradual dissipation of energy. So we had the idea of friction blocks under the spillway of dams. So we thought we should have some kind of friction blocks, as you can see here, a number of rows of friction blocks. But these friction blocks should have a limit on its height, so that height was restricted to only 0.8 meters, wherein this can facilitate people who visit the beach can sit and relax and enjoy the beautiful beach. And only during extreme events, these buffer blocks will serve as buffers. So the buffer block size was taken up from Petrika from 1984. This slide shows on the left side you have the experimental physical model, showing the effect of the buffer blocks. On the right side, you see the numerical modeling of the buffer blocks flow interaction. And then based on this, we went ahead and then now, prior to doing this, we looked at the real-time scenario. Before taking up the studies, we looked at we checked the average human height, men and women, and the average human sprinting speed, both women and men, and then all these things were incorporated while modeling the flow structure interaction problem, and based on which we try to we have done the work is still going on, and we try to also change. We have been changing the spacing between the blocks, the lateral spacing of the blocks, as well as the spacing between the rows of the blocks, and also the shapes of the blocks. So this is going to be an interesting work, and some of the publications have already been published in the within this year. I think we have two or three publications, and then so these are all the references for any information. Please don't hesitate to contact us. And before I then challenges and way forward. Challenges are the high capital cost, regulatory overlaps, balancing ecological trade-offs, people participation, very very important, because we had a lot of experience by interacting with the local coastal community, and that is very very important. Then next is way forward. Pilot projects have to be taken up when we are looking at the kind of problems I had discussed. The that also necessitates interdisciplinary R&D. International collaborations are very important. We have been interacting with a number of German universities on this problem. Then mainstreaming nature-based and engineering solution. And before I thank you for your kind attention, I would like to thank my co-workers, my former students, and all those who have been involved in my work. Thank you very much.